Modern urban areas provide all kinds of facilities, such as roads, public transportation, and parks, which significantly improve the convenience of our daily life. Human activities in urban environments are also diverse. There are lots of motor vehicles running on the road every day. People do all kinds of exercise outdoors, such as cycling and running. These human activities generate various kinds of seismic waves, which propagate in the Earth's near surface. We can use seismic sensors to collect the seismic waves generated by human activities. If we bury seismic sensors at the roadside, they would record seismic signals such as traffic signals, footstep signals, and even the sound generated by an airplane engine. Take traffic signal as an example. When a car is running on the road, it can be taken as a moving source, which constantly generates seismic waves. The seismic waves then propagates in the near surface and then reflect back. These seismic waves can be recorded by a seismic sensor buried in the soil. This figure shows the 20-second-long seismic data, which contains a traffic signal which is generated by one motor vehicle and its corresponding energy distribution in the time-frequency domain, which we call spectrogram. I select 3 times on the spectrogram and label them as A, B, and C. A represents the car is approaching the sensor, and it starts to generate enough energy to be recorded by the seismic sensor. B shows the car arrived at the sensor, and that is why the energy of the recorded signal is the strongest at this point. And C shows the car is leaving the sensor, and the energy starts to be not strong enough to be recorded by the sensor due to seismic attenuation. The decrease in amplitude of the seismic wave is called seismic attenuation. The waves are largest where they are generated, and gradually get smaller as they move away. With this free and easy to collect seismic traffic signals in the urban environments, we want to identify the isolated traffic signals and extract the seismic attenuation over time from them to see if they vary with time. Besides, we want to explore what are the factors that may cause these variations. Since the seismic attenuation carries the information of the underground, we give 3 potential factors that may cause the changes of the underground properties, which are rainfall, traffic count, and the temperature. The last 2 factors are the main factors, which may change the pavement health. For the field data, we deploy the seismic sensor at 2 roadside sites, which are NUS Exit and the West Coast Highway. And the third one is in the West Coast Park, which is about 7 meters to the roadside outside the park. Now let me show you some field data. These 3 figures show 1 minute seismic ambient noise and its corresponding spectrogram recorded at the 3 sites respectively. The traffic signals recorded at the NUS exit is relatively clean. However, for the heavy site, the data is seriously contaminated by the noise generated by engines of big trucks. For the park site, the traffic signals are seriously attenuated due to the large distance between the sensor and the road. Now let's see the results. We process about 7 months long seismic ambient noise data for all 3 sites. This figure shows the results for the NUS exit site. The extracted seismic attenuation and rainfall have similar variations, while it has opposite variations with the temperature. However, it is hard to observe the correlation between the seismic attenuation and the traffic count. This figure shows the results for the heavy site. We can obtain the same conclusion as the NUS exit site. However, for the park site, the extracted slope is not correlated well with all the potential factors. We will discuss this later. The correlation coefficients between the estimated seismic attenuation and rainfall at NUS and heavy sites are 0.67 and 0.64 respectively. The corresponding time lags are 1 and 2 days for these 2 sites respectively. However, it is hard to determine if the seismic attenuation is influenced by traffic count within such a short time period. Although the correlation coefficient between the slope and temperature is big, it is also inconclusive whether temperature changes pavement properties sufficiently to include changes in the mild seismic attenuation, since the variation of temperature in Singapore is small and it is highly correlated with the rainfall, with a maximum correlation coefficient of 0.67 at lag 0. For the park site, if we look at the result more closely, for example, this part, we can observe two main peaks on the estimated seismic attenuation and the rainfall curve, respectively. The time lag between the first peaks is small, while that between the second peaks is large. If we look at the rainfall, there was almost no rain about 15 days before the first peak, and thus rainwater can quickly seep into the underground. However, between the first peak and the second peak, there was only 1 week when it almost didn't rain. As there is a lot of vegetation in the park, the water in the soil is hard to evaporate, and thus it takes more time to infiltrate the rainwater occurred at the second peak. And we can find another part in the data with the same phenomenon we just talked about.